Many laboratory procedures require sets of solutions that cover a range of concentrations. These solutions are created using the process of serial dilution. To begin a serial dilution, a small volume of a concentrated solution is transferred into a new container. Then diluted with additional solute. This is made into a serial dilution by repeating these steps several times using each new dilution as the starting point for the next one. The end result is a set of solutions whose concentrations vary in a uniform way, with the concentration of the solution in each container lower than the one previous. Working through a set of dilutions illustrates how the concentration changes in a uniform way across a dilution series. In this example, we start with a stock solution that has 100 millimoles of a compound and make a series of 10x dilutions. The first step is to fill the first container with 10 mils of the stock solution. 100 millimoles in 10 mils of solution makes the concentration in the first container 10 molar. For the first 10x dilution, 1 mil of the stock is transferred into the next container. At this point, we still have 10 mils of the original solution. 9 mils are in the first container and 1 mil in the second. The concentration is the same in both containers. This concentration will not change until the second container is diluted with the addition of 9 mils of solute. With the solute, the volume of the second container is 10 mils and the concentration is dropped by a factor of 10 from 10 molar to 1 molar. The second container is then used as the starting solution for the second 10x dilution. Transferring 1 mil from container 2 to container 3, then adding 9 mils of solute creates the second 10x dilution. Doing this 4 times results in 5 containers, each containing either 9 or 10 mils of solution. The concentration of each is 10 times less than the previous. In the end, we have a dilution series that covers 5 orders of magnitude from 10 molar to 1 millimolar. The number of steps and the dilution factor can be varied depending upon what is needed for a particular application. Dilution series give very uniform results when working with well-mixed chemical solutions at molar concentrations. Results are more variable when the starting solution is a well-mixed suspension of particles as opposed to a mixture of dissolved molecules. The reason for this is that a well-mixed solution of molecules at concentrations in the molar or millimolar range have billions upon billions of molecules in each milliliter, while a suspension of particles often have relatively dilute concentrations of only thousands of particles in the entire volume. So, no matter how well mixed the suspensions are, they remain patchy enough that the dilution series is rarely perfectly uniform. If we start the dilution with 1,000 particles and do the same 10x dilution steps, the first container, when filled with 10 milliliters, has a concentration of 1,000 particles per 10 mils, or 100 particles per mil. To do a 10x dilution, 1 mil is transferred to the second container. In theory, we'd expect there to be exactly 900 particles in the first container and 100 in the second. Because the suspension is not perfectly uniform, we transfer 102 particles. As a result, the concentration in the first container is now just under 100 particles per mil, and the concentration in the second container is just over 100 particles per mil. When 9 mils of solute are added, the final concentration becomes 10.2 particles per mil instead of the expected 10 particles per mil. As we continue to do the 10x dilutions, the divergence from the theoretical values continue. The transfer from the second to the third moves 13 particles instead of the expected 10. With 9 mils of solute added, the third dilution in the series has a concentration of 1.3 particles per mil. 1 particle is moved from the third to the fourth container, resulting in a final concentration of 0.1 particle per mil. Since the concentration in the fourth container is less than 1 particle per milliliter, we have a very good chance of not transferring any particles to the final container. This is a common occurrence during many assays, including culture-based methods for estimating bacterial cell density, such as plate counts or most probable number estimate. Assays that rely on standard curves include real-time PCR, quantifying the number of bacteria in samples using plate counts, as well as a variety of quantitative colorimetric, radiometric, and enzymatic assays.